Welcome to the Predictive Analytics Regression and Classification course. In this lecture, we are going to discuss how a categorical variable as predictor is going to play in the linear model setup. And typically, these models are sometimes called ANOVA, and in a special case, it's called ANOVA. But overall, it is part of the linear model setups, and regression also is part of the linear model setup. First, we will consider an experiment. So suppose an experiment is performed to assess the relative effect of three toxins and a control on the liver of a certain species of trout. Trout is a particular fish, a particular species, and the effect of toxin on that particular fish that is being studied. There are about amounts of deterioration of the in standard units of the liver in each sacrificed fish. So you can see there are three toxin levels, type of toxin 1, toxin 2 and toxin 3, and then there is a control group where no toxin is being given, and the level of deterioration of the liver condition is being studied. So there are four in each group. There are four fishes, specimens. So total there are 16 observation. Like in each group there are four. So there are four groups, 3 treatment group and 1 control groups. Now we want to develop a model which will affect the treatment effect. So what the simple model that we can think of, that Yij, I stands for ith group. In this case, I equal to 1 to k, but k will be, for our case, is 4 because we have 4 groups. And J runs for within a group how many samples we have. Here we have in each group we have 4 samples, but you can have different number of samples. So that's why J runs from 1 to up to Ni. Ni is the number of samples in the ith group. So the model that we are thinking is Yij equal to theta I plus epsilon Ij, where expectation of epsilon Ij is 0 and variance of epsilon Ij is sigma I square, for where sigma I square finite, and covariance of epsilon I j and epsilon I dash j dash is 0. So that means basically we are assuming that each there is no correlation between each of the samples. Each of the samples are independent. If you assume that, then covariance of epsilon Ij and epsilon I dash j dash will be 0. So little bit more clarification of the model. We can take sigma I squared to be different. But for simplicity, we are assuming sigma I squared is equal to sigma squared for all groups. So all group has the similar variance. So this assumption is called homoscedasticity assumption. And then we assume that epsilon Ij is following normal distribution with mean at 0 and variance sigma square. So this is the model setup that we are going to work out. So this is from the model we are framing, from the experiment we are framing the model. Now as we frame the model, question is, can we express this model into linear model form, like y equal to x beta plus epsilon? Then we will have an analytic solution of the above model. This model will have an analytic solution. So first we have to define the X matrix or the design matrix. So we have 16 observation for, you can see there, so we have 16 rows. Yeah, the first four rows of my data belongs to toxin group 1, and rest of the places called toxin 2. For the toxin 2 I created zeros, toxin 3 I created 0, and the control group zeros. Similarly, the from row 5 to row 8 I have toxin group all ones, toxin 2 goes to 1, then 3 is 0, and control group from row 5 to row 8 is 0. This is called dummy creation of dummy variable in statistics. In machine learning, often it is called one-hot encoding. This is very useful. This one-hot encoding is very useful solving many problems, and we will see soon how it is going to make our life very simple. So we have 16 rows for each samples. We have one representation, and if it goes to toxin 1 we have 1. If a particular row does not belong to that group, then that row will get 0. All the observations are stacked over another. The first 4 row observations belongs to toxin 1. From 5 to 8, observation number 5 to 8 belongs to toxin group 2. From 8 to 12 belongs to toxin group 3, and from 13 to 16 it group belongs to control group. Then we calculated X transpose X. Turns out X transpose X in this case become very simple. If you go back to the X, what happens is X transpose X is essentially X transpose is kind of, when it is first row, first column will be just it's with itself. So it will have create a 4 and then 0, 0, 0. In this way, the X transpose X creates this matrix. So X transpose X inverse is very simple. Just diagonals will be 1 out of 4 and the off diagonals are all 0. So this is simple solution. Now we calculate X transpose Y. X transpose Y is, if you look at carefully, that sum of the first group of observations, the second element is the sum of the second group of observation, and third is the third group of observation, and fourth is the fourth group of observation, fourth element. Hence the solution is X transpose X inverse X transpose Y. X transpose X inverse is all diagonal elements is 1 by 4 and off diagonals are 0. So my beta hat is basically sample group mean y1 bar of the first group. Similarly, y2 bar is the sample group mean of the second group of the toxin group 2. y3 bar stands for the sample mean for the group 3, in this case toxin 3, and y4 bar is the sample mean of the control group. So model yields group sample means as the solution for theta 1, theta 2, theta 3 and theta 4. So this is very interesting solution. Now I am posing a question to you guys. Ask yourself, how to model global mean? The above experiment is being modeled as yij equal to theta I plus epsilon ij, where I equal to 1 to k and j runs from 1 to ni, where each theta I is the group mean. We realize that each of the theta I is the group mean, but how can we model a global mean for the all data? So we also want to incorporate global mean for all data. In this situation, I would like you to take a pause your video here, for about 10 minutes. Think about it and try for yourself to develop the model with global mean. I believe you have now got a possible solution. Let us see how can you solve the solution, get a solution. If one possible solution is you take yij equal to mu is the sort of a global mean, plus theta I are the group means, plus some epsilon ij. Now I equal to runs to 1 to k and j equal to 1 to ni. This is a simple solution looks like, but we are going to face a problem. Can you identify the problem? So again, I will request you to pause the video for a while and think about maybe for 10 minutes that what problem you are going to face this particular model. I believe now you have got the idea that what problem you are going to solve, you are going to face, and we know that in this case our response vector will still be same. The change we will see, if you look into the model, our response vector will going to be same. The only change that we are going to see is in the design matrix. So the change is that whatever design matrix we have had before, that same design matrix we are still going to have. But now what we will have is we are going to have a fifth column called intercept. Okay, so we are going to have an intercept column. Now this is an interesting phenomenon, that if we have this design matrix, then our x transpose x matrix is going to be 16 4 4 4 4 and then 4 4 0 0 0, then 4 0 4 0 0, 4 0 0 4 0, 4 0 0 0 4. In this matrix, if you look at very carefully, the first column of this x transpose x is actually direct sum of second column, third column, fourth column and fifth column. So if you just add the second column, third column, fourth column and fifth column, you will get the first column back. So the first column is completely dependent on the second, third, fourth and fifth column. So that means x transpose x is not going to be invertible. That means solution does not exist if we create a dummy variable for each labels of categorical variable. I hope you understand the problem. Let me repeat. Let me go back to the model. In this model, what we have only effectively one predictor. Predictor is treatment, and there are 4 possible labels of the treatment: toxin 1, toxin 2, toxin 3 and control. So for each labels of the treatment, so there is only one predictor, that is treatment. In treatment label there are 4 possible labels, so one categorical variable with 4 labels: toxin 1, toxin 2, toxin 3 and control group. For each label, if you create a for each label you create a dummy variable or one-hot encoding, then what happens, if and also you keep intercept parameters, then in the X matrix the intercept parameter becomes completely dependent on all the columns of your predictor variables. As a result, one column will become completely dependent on some other columns, and hence we will not be we are not going to have an invertible matrix or going to have an analytical solution at all. For this case, solution does not exist. So you have to be very careful about when you are going to handle categorical variables with different labels. Let us stop here and we'll continue on the next part.